Okay, today we're going to be talking about pneumatic thermostats. Specifically, this is going to be a Siemens thermostat, part number 192841. This is a pneumatic thermostat, and it is a reverse acting thermostat, which means that the output pressure works inversely in correlation to the temperature. So as the temperature goes up, the pressure goes down. This is what the actual thermostat looks like out of the box, and you can adjust the temperature setting once it's plugged in with the thumbnail down here, and it tells you what temperature the room the set point is, and this here tells you what temperature the actual temperature is in the room. On the back of the thermostat there are two places for you to connect your pneumatic tubing, and the bottom one is the supply and the top one is the branch. So the bottom one is going to be a constant about 20 psi pneumatic input to the thermostat, the pressure input, and the output from here will go to whatever the thermostat is controlling. Now, in the building that I'm currently working in, most of the building is where the thermostat directly controls a damper motor, and this is an old one that's bad. The diaphragm has failed, but this is exactly what they look like. The spring range on this damper motor is 3 to 8 psi. So in other words, when there's no pneumatic pressure back here, the shaft will be retracted all the way because it's under spring tension. As the pressure inside here gets up to 3 psi, the shaft will begin to extend out. And at 8 psi, it will be fully extended. 8 plus psi, it will be fully extended. Now, the way that these pneumatic in this particular situation, with these spring ranges 3 to 8 psi, this pneumatic thermostat can send out 3 signals. Now the 3 signals that it can send out are either going to be full cold, modulated, or full heat. Now because it's the damper motor is a 3 to 8 psi spring range, so if the thermostat has an output pressure somewhere between 0 and 3, it's going to be a full cold signal because the shaft is going to be in the fully retracted position, and as much air that the damper box will allow will be passing into the room. So that would be a full cold signal. Now if the pneumatic signal was somewhere between 3 and 8, the shaft on the damper motor would be somewhere between its fully closed and fully open position, so it would be in a modulated state. So I use the word modulated, or you could say it's in a middle state. It's not fully opened, it's not fully closed, it's somewhere in between, depending upon what the exact pressure is. If the pneumatic signal from the thermostat is 8 plus psi on the output pressure of the thermostat, well, at that point your zone is in full heat. So these are the 3 conditions that this thermostat, with this very simple zone with just controlling a 3 to 8 psi spring range damper actuator motor, these are the 3 signals that in this case that you can achieve out of the thermostat. So now how do you calibrate this thermostat? And the answer is, because this thermostat is controlling a damper motor, which is 3 to 8 psi, you want to calibrate the T-stat so when the T-stat is set to room temperature, when your set point is set to room temperature with an external, now even though this has the room temperature on it, I don't use this in order to calibrate this thermostat because in my opinion that's not accurate enough. Although this is very accurate, I'll still go ahead and get a digital thermometer. In my case, I use a field piece meter, which measures temperature degrees Fahrenheit, and I will get the room temperature from that, and that is highly accurate. And I'll put that I'll put the sensor, the thermocouple sensor of my field piece, very close to this bimetal strip, because this is the actual strip that tells that's monitoring the temperature of this. So I'll put it there so they're actually receiving the exact same temperature. And then once I know that temperature based off of my field piece, let's say hypothetically the room is 73 degrees Fahrenheit. In this case, you set your set point to 73, which is right there on this reverse acting thermostat. Then I'm going to go ahead and I'm going to take a 0 to 30 psi pressure gauge with the appropriate tap for this Siemens thermostat. I'm going to put it where in the correct calibration hole right there, and then I'm going to see what that pressure is. And now that pressure, what I want it to be is 5.5. And the reason why I want 5.5 is because that is the midpoint position of what the thermostat is controlling. The thermostat is controlling a 3 to 8 psi damper motor. The midpoint of this is 5.5. So at room temperature, at 73, if the room temperature right now is 73, I set it to 73 and I set the pressure here at 5.5. Now if the pressure is not 5.5 on the output, what I'll do is I'll take this wrench that comes with the thermostat kit, and there's a black screw underneath here, and you will either turn it to the right or to the left to either raise or increase the pressure to calibrate it to exactly 5.5 in this particular case. So that is how you calibrate this Siemens thermostat. Other thermostats, it may not be Siemens, it could be Johnson Controls, Robert Shaw, could be very similar, but the same process will pretty much take place. You want to set the calibration of the thermostat to the midpoint of whatever it is controlling. Alright, so here I have an actual reverse acting thermostat on the wall, plugged in. I've got my field piece. This particular meter is model SC77 because it's got backlight. And I've got the thermocouple sensing device for the temperature. I've got the meter set at temperature here. And the temperature close to this bimetal strip is approximately 74 degrees Fahrenheit. So okay, so now we know that it's 74 degrees Fahrenheit. So I'm going to set this to 74, and I know you can't read it from your angle, but the pressure on here says 9.5 psi. So this thermostat is out of calibration because the room temperature is 74. I've got the set point set at 74, and the pressure on the gauge says 9.5, and it should be reading 5.5 because this thermostat is just controlling one of these damper motors with the 3 to 8 psi spring range. So I'm going to take this tool, because the pressure is high, I'm going to turn it counterclockwise. There's a screw behind this plate. You can't see it from your angle, but you just put it in, and I'm going to lower it to 5.5. Now to verify that adjustment, what I'm going to do is I'm just going to go bring the pressure down, bring the pressure up, and then go back to 74 to see if I've got it. And yes, that looks good. And I actually want my room temperature to be 72. So I'm going to lower the set point to 72 now that it's calibrated. And the pressure has dropped down to 0. Well, this is a reverse acting thermostat. The thermostat can send out 3 signals. 0 to 3, if you recall, is full cold, which makes perfect sense because the room is 74 degrees. I just set it to 72. I need all the air coming into the room because I need to be at a full cold signal. So that is operating as it should. So the damper right now with the 0 to 3, the damper motor, which is right here, is going to be retracted all the way, and the full airflow is going to be entering now into the room in this particular condition. All right, now in a lot of office buildings, the thermostat, which is this pneumatic device right here, doesn't go directly to the damper motor. What it does is it goes to a velocity controller, then from the velocity controller it goes to the damper motor. Now, if the office building had a reverse acting thermostat, which is like this, and you used a velocity controller, the correct part number would be a CSC 3021-10. This is the correct velocity controller to use when you have a reverse acting thermostat. Now, on that velocity controller with that part number, this is a velocity controller I'm holding here in my hand, the reset start point is 3 psi with a span of 5 psi. So you're going to calibrate the thermostat, the reverse acting thermostat, exactly the same way you would if it was controlling this damper motor 3 to 8 psi, because this has a reset start point of 3 to 8 psi with a span of 5, which is identical to the action of the damper motor in this particular case with a reverse acting thermostat. So it's a reverse acting going to the velocity controller. If you used part number CSC 3021, it has a reset factory start point of 3 psi with a span of 5 psi. Those are the factory settings. You're going to calibrate the pneumatic thermostat exactly at 5.5, exactly the same way. Okay, so now let's talk about an office building that uses a direct acting thermostat. They look exactly the same as a reverse acting thermostat, but the model number is different. The model number for direct acting is a 192-202 for a Siemens thermostat that looks just like this. On a direct acting thermostat, as the temperature goes up, the pressure goes up. So it's directly proportional. Now, in that particular case, if your direct acting thermostat was controlling a velocity controller, the velocity controller that you're going to control is going to be a CSC 3011, which is right here. If you want to zoom in on that part number right there, it's a CSC 3011. That is the correct velocity controller to use when you use a direct acting thermostat. Now, how do you calibrate the direct acting thermostat with this different velocity controller? Well, you need to look at the spec sheet on the velocity controller. On the CSC 3011, the reset start point is at 8 psi with a span of 5. So, in other words, it would be just like controlling a damper motor with an 8 to 13 psi spring range. And you want to calibrate to the exact midpoint of between 8 and 13. Well, in that particular case, you're going to calibrate the thermostat at room temperature to 10.5. This is if you have a direct acting thermostat and the thermostat is controlling a velocity controller, which is the CSC 3011, which has a factory reset start point of 8 psi with a span of 5 psi. The T-stat in that case is going to be calibrated to 10.5. And I'll show you how all that comes into play in the next segment. Okay, so now let's talk about an office building that uses a direct acting thermostat. They look exactly the same as a reverse acting thermostat, but the model number is different. The model number for direct acting is a 192-202 for a Siemens thermostat that looks just like this. On a direct acting thermostat, as the temperature goes up, the pressure goes up. So it's directly proportional. Now, in that particular case, if your direct acting thermostat was controlling a velocity controller, the velocity controller that you're going to control is going to be a CSC 3011, which is right here. If you want to zoom in on that part number right there, it's a CSC 3011. That is the correct velocity controller to use when you use a direct acting thermostat. Now, how do you calibrate the direct acting thermostat with this different velocity controller? Well, you need to look at the spec sheet on the velocity controller. On the CSC 3011, the reset start point is at 8 psi with a span of 5. So, in other words, it would be just like controlling a damper motor with an 8 to 13 psi spring range. And you want to calibrate to the exact midpoint of between 8 and 13. Well, in that particular case, you're going to calibrate the thermostat at room temperature to 10.5. This is if you have a direct acting thermostat and the thermostat is controlling a velocity controller, which is the CSC 3011, which has a factory reset start point of 8 psi with a span of 5 psi. The T-stat in that case is going to be calibrated to 10.5. And I'll show you how all that comes into play in the next segment. The building has a direct acting thermostat. The direct acting thermostat is controlling a CSC 3011 velocity controller. So we know that the CSC 3011 velocity controller has a reset start point of 8 psi with a span of 5 degrees Fahrenheit. The midpoint of that is 10.5. So your calibration is going to be 10.5 at room temperature with the direct acting thermostat in this condition. Now, also, the direct acting thermostat puts out 3 signals in relationship with this velocity controller. What are those 3 signals? Well, it's either going to be 0 to 8, which is full heat, or 8 to 13, which is modulated or somewhere in the middle, and 13 plus, which is going to be a full cold signal. That's going to be the 3 different signals that direct acting thermostat can send out to that velocity controller. Now, ideally, you want your customer to be between 70 and 75 degrees Fahrenheit with an ideal setting room temperature of 72.5. If you have 72.5, or if you're in between 70 and 75, you've met your requirements. You've got air conditioning for your customer. You're within building set points that the original architect has designed. The mechanical engineer who designed the building has designed it in such a way that you should be able to have these temperatures. If indeed you are outside of these temperatures, you probably have something wrong. Your thermostat's not working right, your velocity control's not working right, your damper's not working right, or something upstream of that, your major air handlers or refrigeration, your air conditioning equipment is not working right, chillers or something like that. Now, let's talk about a real-world example on how we can maintain this temperature with this thermostat and with the CSC 3011 velocity controller. Let's say that you have a room temperature of 72 degrees Fahrenheit. That's the actual room temperature. If you're at calibration on your thermostat, your pneumatic signal output is going to be 10.5 psi. Now, these thermostats, they come factory set with a sensitivity of 2.5 psi per degree Fahrenheit. It's adjustable if you wanted to by this slide bar right here, but you're better off leaving it at the factory setting, because the factory setting is a great setting, and you'll see why as I demonstrate that through what happens. If you're at room temperature, your room is at 72, your pneumatic output signal is at 10.5, your velocity controller is modulated, sending a modulated signal out to the damper actuator. Now let's say that the room temperature begins to get colder. It goes from 72 down to 71. The thermostat is going to sense that we've dropped 1 degree Fahrenheit, and because the sensitivity is 2.5 psi per degree Fahrenheit, the pneumatic signal going to the velocity controller is going to get smaller by 2.5 psi. So you're going to go from 10.5 down to 8. Well, if you remember, now we're going from the modulated stage to just the beginning stage of full heat, because that's right there in the middle. Let's say the room still gets too cold. You're going to drop 1 more degree Fahrenheit, and now your signal is going to go from 8 down to 5.5. Well, now clearly you are in a full heat stage as far as the damper actuator is concerned. That damper actuator is going to be fully retracted once you go from 71 down to 70. It's going to reach its full maximum. Now let's go the other way. Let's say you're at 72 and the room gets too warm. There's not enough cold air coming in. Well, in this case, you're going to go and your thermostat's going to go from 72 to 73. The pneumatic output signal is going to go from 10.5 to 13. Well, at 13, you're at the top end of the modulated scale, and at 13, you're at the beginning end of a full cold signal. So you're just about getting ready to have that damper full opened. If you go 1 more degree Fahrenheit down to, up to 74 degrees, the pneumatic output signal is going to be 15.5. So in that case, you are clearly at a full cold signal. The damper actuator motor is going to be opened as 100% unless you have it restricted by the velocity controller. These velocity controllers do give you the option of controlling what's referred to as the minimum and maximums. So you can actually control them. But outside of, let's just say that for the sake of this training session, you have the maximum set to 100%. Well, at 74 degrees Fahrenheit, your damper will be opened 100% as long as you don't have it restricted here in the velocity controller. I'll go over the velocity controller in a different segment. I want to discuss, if this was an interior zone, you would be done. This is all that would be happening, because let's say that your particular building has no heating on the interior zones, but what about if it's an exterior zone? Well, it's very common to have perimeter reheat. So what you have is you have a couple of hot water boilers or hot water heaters, however you want to refer to them as, because they're not generating steam. All they're doing is heating up water to about 190 degrees Fahrenheit. They're going to circulate that water around the building, and then on the exterior zones, you're going to have a coil controlled by a hot water valve. Now, all right, now we're going to talk about the complete system on how the thermostat is reacting with the box, and if it's an exterior zone, how it's going to control a hot water valve. Now, here's a hot water valve. I purchased this particular one from RSD in Lake Forest. Now, the spring range on this one here, it was you could put in a different spring if you wanted to, but for us we put in the 5 to 10 pound spring range. And I'm going to show you how this is going to correlate with the direct acting thermostat on a system and how the hot water is going to work. So this would be, if you have hot water, your outside air temperature should be approximately 58 degrees Fahrenheit or less. The way we've got this particular building set up, when the outside air temperature warms up and it gets above 58 degrees Fahrenheit, the boilers shut off and then the pumps shut off 30 minutes after that. So you've got a cold exterior on your building, you're below 58 degrees, you need heat on the inside of the building. Here what we do is we heat the perimeter zones only, so the zones that are touching the exterior of the building. The interior zones don't have this. So in the exterior zone, the VAV box is going to have a coil, copper coil, and it's going to be controlled by a hot water valve, which is controlled by the signal which is coming ultimately from the thermostat on the wall. So in this case, where you have a direct acting thermostat, remember there are three different sensing, the thermostat can send out three different signals. It's either going to be full heat, full cold, or somewhere in the middle. Now, with in this case, the direct acting thermostat is talking to the velocity controller. Reset start point on that was at 8 with a span of 5, and that's why we're going to calibrate it to 10.5. So now let's go back to our room example here, where the room is 72 degrees Fahrenheit. Mind you, we want to keep the customer between 70 and 75. The room is 72 degrees Fahrenheit. You're at calibration, which means that the pneumatic pressure going to the velocity controller is 10.5. That pressure is also going to this hot water valve. That same pneumatic pressure is going to the hot water valve. Well, this is a 5 to 10 pound spring range, and it's a normally open valve. So if it's at 10 pounds or higher, the valve is closed. So at 10.5, this hot water valve will be closed, and you're going to be right in the middle stroke of your damper actuator on the airflow. Now, let's say that the room, because it's cold outside, it's going to start getting cold on the inside, and your room goes from 72 down to 71 degrees Fahrenheit. Now let's go through and see what happens. We already know that the sensitivity adjustment on the thermostat is 2.5 psi per degree Fahrenheit. You've dropped 1 degree Fahrenheit, so you're going to drop 2.5 psi. You're going to go from 10.5 down to 8. Well, now what happens to your box is now going to go more towards the closed position, more towards the minimum airflow position. What happens to this hot water valve? It has a 5 to 10 pound spring range. Well, once this pressure got anything less than 10, the valve began to open. So at 8 pounds, this valve is opened about 40%. So now you've reduced your airflow, and you've got about 40% of hot water traveling through your coil, heating up that air, trying to keep that customer comfortable. Now let's say that it still gets cold, and it's still getting colder, and you drop another degree Fahrenheit, and you drop all the way to 70 degrees Fahrenheit. The pressure is going to go from 8 to 5.5. Well, now your hot water valve is almost fully open because it's a 5 to 10 pound spring range. That customer is now going to have minimum airflow with just about maximum hot water going through that coil, and you're going to have probably about 100 degrees Fahrenheit or so coming out of the registers. You want the space temperature to be 70. You're feeding it with 100 degree Fahrenheit air or thereabouts, and you're going to warm up that space. And so eventually this is going to start coming back the other way, and you're going to keep that customer within this range. You're doing all that you can for the customer. You're giving the customer minimum airflow and maximum hot water. If it dropped even just a little bit below 70, a little bit more, you'll be at 100%, but usually even at 5.5, you're going to get the maximum out of that valve and out of that coil anyway. So you're going to be giving them a full heat signal right at 70 degrees Fahrenheit. So again, you're going to be able to keep this customer within that. And I just want to explain how that worked with the hot water valve.